everybody to my 9th lecture today. Again, we talk about climate change, and this time I would like to focus on feedback mechanisms. So let's start with an interesting diagram. This shows you the temperature of planet Earth, and it's shown in this time scale here, which is a bit complicated. So on the right side you have 0, this is today. Then you have a linear scale of the last 20,000 years. Then you have a compressed scale, again a linear scale of the last 1 million years, so 1,000 times 1,000 years. And then further on the left you have a logarithmic scale. It goes from the first million years to the second, the third, and then up to 500 million years before today. And plotted is the temperature in a scale which is 0 at the average between 1960 and 1990. And this temperature difference then shows us how the temperature average was compared to today, basically. On the very right you see approximately 0. In the last, let's say, 10,000 years we had almost the same temperatures. Very stable situation, very nice weather. In the last years temperature is rising, and at the very right on the end of the scale you see that the predictions for the next 50 and 100 years are that temperature is rising. That is what we call the anthropogenic global warming, but we will come later to that. So if we go from right to left further, then we see there is a drop, which is a cold period of an ice age. And then we jump to the compressed scale, and there you see all the warm and cold periods, so the glacial periods and the warm periods. And these are the different ice ages we had in the past. And there you see also a quite regular structure. So the last 800 to 1,000 times 1,000 years, so almost since 1 million year, temperature of the planet Earth is basically constant, but it has a very nice regular structure. Below I showed you where mankind started. Since about 200,000 years mankind, so Homo sapiens, is on the Earth. So Homo sapiens had already 2 cold periods, but otherwise it was a quite constant temperature. The fossil fuels started only in the last about 100 years, so that is on this scale only the last line which you see. If we go further to the left, we see the temperature was warmer and warmer the further you go to the past. It had a maximum about 50 million years ago, and then it went down and up and down and up and so on. So in the very far past of the Earth there was quite some changes in temperatures. I also showed you where the coal production was mainly happening in the carbon area. I showed you where the dinosaurs appear and where they got extinct. Also this period was quite warm at this time. Then it got really much warmer and then colder again, and that is the development of the Earth. Of course, if you go to the very beginning, the Earth was really hot, much higher of course than all these temperatures shown here. But I show you the plot to show you that for the lifetime of the human beings, temperatures have always been quite the same as today, and the changes of temperature in the last 1 million years were quite small. So let's focus on the earlier times. So here on this plot you see the last 800,000 years in an expanded scale, and there are quite a few different curves here which I want to explain in a bit more detail now. First of all, have a look at the red curve. The red curves gives you the temperature in the tropics. This is the tropical sea surface temperature. Basically, it has a variation of about 2 to 3 degrees of Celsius. Below you see the Antarctic temperature based on ice cores. So this is at the South Pole basically. Then below that you see the temperature in the deep ocean deposits. So in physics you have the possibility to look at certain isotope relations. In this case you look at oxygen-18 isotopes, and from that you can get information about the temperature at these times. So there are 3 temperature curves which basically all are correlated. They look to some extent very similar in the last 800,000 years, and it shows you that the average temperature on the Earth is basically well understood and well checked against each other by 3 different methods. So the variations are quite moderate, 2 to 3 degrees, but you see this up and down all the time. This up and down, of course, are what we know from history as the ice ages. So there are warm and glacial epochs during that time. That means that sometimes the North and South Pole had a lot of ice and sometimes very little. The plot at the very bottom here shows you the sea level variation. So you see the sea level is coinciding with the temperatures, and this of course is also natural because you know during a glacial period where there's a lot of ice, like all Northern Europe is under ice, then of course there's less water available for the oceans, so the sea level drops, and in hot periods the ice is melting and the sea level rises. The thing you should remember here is the sea level variation is about 100 meters. So it's not a few centimeters like you see it today. It is really 100 meters higher or lower depending if there's a glacial period or a warm period. So this is a huge effect for our living here on this planet. Now let's come to the upper curve. The upper curve, the green one, is the CO2 concentration. So also here you see it's going up and down, and it is correlated to the other plots, which means that during warm periods there's a high CO2 concentration, and during cold periods there's a small CO2 concentration. This was always very stable, so it had a value of about 240 ppm plus minus about 80 ppm. So it's really small variations over 800,000 years. So long before man arrived 200,000 years ago. And the important point now is that due to our fossil fuel consumption, CO2 is rising strongly, and you have seen that in previous plot, in the previous lectures. Today we are at about 410 ppm, and the tendency is rising all the time. So if you don't do anything against it, this curve will rise. Now, of course, the question is, what is the reason for the correlation between CO2 and the temperatures? The correlation between temperature and sea level is easy to understand. This is the glacial ice which is melting. But what about CO2? Of course, somebody knowing about greenhouse gases knows that when there is more CO2 in the atmosphere, the temperature will rise. On the other hand, why should the CO2 increase at the warm periods, and why should it go down in the glacial periods? So one question here is, of course, what is the cause and what is the effect? Is the CO2 the cause, or is the temperature the cause? We will come back to that. Now we come to the next set of curves, which are the top 3 curves in gray or black. These are curves which describe the movement of the Earth around the Sun. You know, the Earth is going around the Sun. In the ideal case, it's just a circle, but in reality, it's not so easy. It's an ellipse which has sometimes larger, sometimes smaller distance to the Earth. In addition, the Earth is rotating around its axis, and due to basic physics laws, this action is doing a precision, so it changes the direction all the time. Then there's the moon, then there are other planets, so the whole solar system in detail is a little bit more complicated than just a circle. But nowadays the nice thing about physics is that you can calculate those things all very precisely, and especially you can calculate exactly at which position the Sun and the Earth were like 800,000 years ago. So these are very straightforward calculations which are known very precisely, and from that you can also calculate the eccentricity and precision of the Earth and the other planets. From that we know that due to the angle which the Earth has compared to the Sun and the distance and all the other effects, the solar irradiation is sometimes a little bit stronger and sometimes a little bit less strong. If you look at these curves which describe these motions here, you clearly see there's a correlation, for example, with the lowest black curve, which has all these wiggles, and the CO2 or temperature curves. You clearly see that always when there are these large wiggles in the third curve, you also have a change in temperature. So there's clearly a correlation between the motion of the planets or the Earth around the Sun and the temperature on the Earth. Now, of course, you can ask again, what is the cause, what is the effect? Well, it's clear from physics point of view that the temperature on Earth has no effect on the motion of the planets. Yeah, the motion of the planets, as I said, is precise for 100,000 and millions of years, and temperature effects on the Earth don't change anything there. So from this point of view, it's clear the correlation, which is obviously in these plots, has to have the following reason. The planets are the reason for the temperature and not vice versa. And this, of course, is also natural. When the Sun changes its angle or its intensity, temperature on Earth can change. This is not really surprising, but this is, of course, very important to understand. These cycles here are called the Milankovitch cycles, and they define the ice ages. So they define the glacial epochs and the warm periods. So this is very clear, and of course all those things have been simulated on computer. And if you look at the curves in more detail, you see there are these dashed pink and violet curves and the dashed blue curves. These are the computer simulation, and they agree very well with the measured temperatures and the measured sea level on our Earth. So in other words, the variations of temperature in the last 800,000 years is basically understood as an effect of the Milankovitch cycles, and secondly, in the complex climate models which people have nowadays, you can quite well reproduce all these effects. So at the first point, there's nothing exciting there. And now, of course, comes the argument: if we add CO2 to the existing climate system, we will add a greenhouse gas, we will increase the temperature, and therefore in future the cycle will not continue the way it did the last 800,000 years, but in future there will be a stronger climate effect and a stronger global warming. Okay, at this point we could end, but of course as a physicist you want to get a better understanding, and there I will show you another few clues which are important. So let's try to understand these curves a little deeper. I showed you they are all somehow correlated, but they are not the same. Myself, I'm a particle physicist, I'm not a climate physicist, so I'm not an expert on all these details, but I have another view on curves compared to some other physicists maybe. So in particle physics, what you always look for is symmetries. all the basic laws have something to do with deeper symmetries which you can discover, and by discovering symmetries you learn something about the physics laws. So if you look at these curves here and you look for symmetry, what do you find? Well, you find something which is very astonishing, and this is what we call in physics time reversal. Symmetry is violated. What does it mean? So look at the curves here. I just take the upper four curves. The other ones I could also show you, but it's just a repetition of the same stuff. If you apply time mirroring, so you count the time instead of forwards, backwards. So what you do effectively is you put a mirror to this curve. From 0 to the left and from 0 to the right is just the mirror image. If you look at the first three curves, the black curves, they obviously are symmetric in time, which means that the Sun-Earth system obeys time reversal. And actually all classical physics systems have to obey time reversal. So if you have a motion somewhere, if you make a video and something is moving, if you run the movie backwards in time, you see the motion in the other direction, and there's a physics law that says that all these basic movements can be inverted without that you can realize that, without that you can distinguish what is forward and what is backward. And the same is it for the Sun-Earth system. It's completely symmetric. If you look forward or backward, you cannot distinguish between the curves. If you now look at the CO2 curve, however, it's different. If you look at the CO2 curves, it's clear. In reality, CO2 rise was very steep, and then it goes slowly down. It goes steep up, slowly down, steep up, slowly down. In the mirror image, it's differently, it's oppositely. It goes slowly up and steeply down. So there's no time symmetry for the CO2 distribution. You can also do it for the temperatures in the other curves. It all looks the same. There is a breaking of time symmetry in the CO2 curves and in the temperature curves. Also in the sea level curves, there's a time reversal breaking. That's how we call that in physics. Where does this time reversal breaking come from? So the cause for the CO2 and the temperature and the sea level is the Sun and the Earth system. But there was no time symmetry breaking. So how can the CO2 curve be violating time symmetry, whereas the cause for the CO2, the motion of Sun and Earth, is symmetric? Well, the conclusion, if you think about it, is because all these systems are classical systems and there's no inherent time asymmetry breaking in these laws of physics, the only reason to understand it is that Earth system must be a system which is strongly nonlinear, so it's not a linear function from the solar system, otherwise it would have to be time symmetric. And the only way it is nonlinear is because there must be very strong feedbacks in the climate system, otherwise you would not get this strong breaking of symmetry. So in other words, the movement of Sun and Earth is just a trigger. This trigger causes the Earth system to change. It becomes warmer, and as soon as it becomes warmer, there's a strong feedback of the climate system to become even more warm. This is what we have to understand. So small changes in the climate system can trigger big effects. And this we want to understand in a bit more detail on the next plot. In climate science, you call that tipping points. So you have small changes at one corner, and due to the feedback loops in the system, you get big effects. So in our evaluation of the time symmetry and breaking of the time symmetry, we found out that a small change in solar irradiation triggers the warm periods after a glacial period. It cannot be a linear function because otherwise, and I repeat myself now, because otherwise the curves would not be so asymmetric. There must be a strong feedback loop. And what kind of feedback loops do we have in the climate system? Well, this is easy to understand. Here, 3 examples. When, for example, the polar ice starts to melt, then the albedo of our planet changes, which means that less light is reflected because the white snow reflects a lot of the light. And if there's less light reflected, then the Earth becomes warmer. And of course, if the Earth becomes warmer, then the ice is melting faster. So there's a positive feedback loop. The more ice is melting, the warmer it becomes, and the faster the ice is melting. Another effect is with the CO2. Because you know that I told you already that half of the CO2 is absorbed by the ocean. If now the ocean becomes warmer, the CO2 is emitted because warm water emits CO2. Yeah, you can study that yourself. If you take a bottle of mineral water and you heat it up, then the CO2 comes out. The same is happening with the ocean. And of course, if the CO2 goes into the atmosphere, there's more greenhouse gas, there's a bigger greenhouse effect, and there's more warming. So the more CO2 there is coming out of the ocean, the more CO2 there is, the more warming you have, and the more warming there is, the warmer the ocean will be, and the more CO2 will be emitted. Also, that is a positive feedback system. Another very strong effect is you have big areas of permafrost on our Earth, like in Siberia or Canada. And when the permafrost regions start to melt, a lot of greenhouse gases come out of the ground, especially methane, which we know is a very strong greenhouse gas. The greenhouse gas is emitted to the atmosphere, it produces greenhouse effect, the Earth becomes warmer, and the permafrost starts to melt faster. Yeah, so these were 3 examples, and there are a lot more examples which show you that whenever you change something in the climate system, there are a lot of reasons why there's a positive feedback loop. And these feedback loops are the reason why the rise of temperature is so fast, whereas dropping the temperature after 50,000 years is very slow. Now we come already to the end of this small lecture, but I think it was very important, and I've never seen it like that in literature, to argue with time symmetry. So what is the conclusion of all that? Well, here again our well-known plot of CO2, this time only the last 400,000 years. We see the strong rise since the industrialization, so the last 50 to 100 years. CO2 is rising rapidly due to the burning of fossil fuels. What does it mean? Well, half of the CO2 will end up in the atmosphere. This makes the greenhouse effect stronger than it ever was. It has never been so high since human beings are living on this planet. So we are coming into an area which we don't know how Earth will react. If we think back to the time of carbon, which I showed you in the previous lectures, there was a steep drop of temperature at the time when, due to photosynthesis, over millions of years, CO2 was taken out of the atmosphere. Now, within not millions of years, but tens or hundreds of years, we take all the CO2 back, and we should not be surprised if we will have a big effect on our temperatures. Half of it end up in the atmosphere. The other half, what is happening with them? Well, they are absorbed by the ocean. What happens to the ocean? Well, the ocean can absorb CO2. You all know CO2 plus water gives carbonic acid. Carbonic acid is, as the name says, an acid. What happens to the marine life if the ocean becomes more acid? Well, there are lots of effects. The easiest one to understand is, there are shellfishes and corals, and they are very sensitive on the pH value. Why is that? Well, simply because if you put an acid on a shell, it is destroyed. So if the pH value is too small, if it's too acid in the ocean, shells cannot live anymore, they get destroyed, they cannot build their shells, and a lot of other animals in marine life as well. So marine life can start dying if the ocean is too acid, and that is what we are just doing to it. So to conclude, since more than 800,000 years, the CO2 value was about 240 plus minus 50 ppm. This was the case in warm and glacial periods, and there is a strong feedback of the two systems. Today we have a CO2 value of 400 ppm, which is higher than at any time when there were human beings on Earth. The last time we had 400 ppm was 3 million years ago. At that time the sea levels were 15 meters higher than today, and the Arctic summer temperatures were about 14 degrees higher than it is at the present day. So even if predictions of our climate system talk only about 1 or 2 degrees, the scale which we must be afraid of is that there are temperatures of like 14 degrees more than today. And of course, I showed you that during ice ages the level of the sea changed by about 100 meters. So we are not talking about centimeters, we are talking about much more in our future. So I want to stop at this point talking about feedback systems from the physics point of view, and next time we have to still work on climate change, but this time we should focus more on the effects that it has on human beings. Thank you, and hope to see you again next time.